Okay, we're trying a new setup. Okay, this setup is working now because the previous didn't. So what I said is that I will talk about the inner product spaces and hot stars next week, and I will finish with the exterior algebra today. So now I introduced a lot of constructions of new algebraic structures out of R modules or vector spaces. So I have the tensor products, the homomorphism space, especially the dual space. I have direct sums. And I showed, especially for dual spaces, that if I have a map from a V to W, I have a dual map from W star to V star. I didn't show that I have, I showed that I have a direct sum map if I have two modules and I sum them and I can sum their maps. I didn't show that for tensor products because I don't need it that much, but I will need for metrics on forms in differential geometry. I will need to be able to form higher dimensional maps in some sense from initial one for the tensor products for the exterior algebra. So I will now define the exterior power of a linear map. Okay, so no, this doesn't sound good. Start with commutative ring with unity, and F VWR modules and file, for instance, or let me write F, doesn't matter. F is a linear map, so F is in linear map from V to W. Then and P is an integer. Now define the map, linear map, lambda P of F by from, so it is from lambda PV to lambda PW, which is the exterior power of, yeah, let's say, the exterior, no, this writes even worse. The exterior power of F bar follows. So the elements of this thing here are sums of monomial by vector. So I will just write for monomials. Some care should be taken to prove that it's unique here and well defined, but we will assume that it is the unique such linear map that such that for any V1 to Vp in V, f of E2, which is A11 E1 plus A21 E2, wedge with A12 E1 plus A22 E2. And we calculated this before. This is the determinant A11. It doesn't matter the ordered coefficients. E1, which E2. And we can prove that in general, that for any V1, V2 in this vector, this space V, we have lambda 2f of E1, which E2 is V1, V2, not only for the basis vectors, is this determinant times V1, which V2. And in fact, this statement holds in higher dimensions. I will only state it. It's very nice theorem. Okay. So as you can see, we get a lot of determinants this lecture. And this is not by chance. Why? Well, determinants, they have some multilinear properties. If you multiply row and add to another, it adds some with some. No, it stays the same. But if you multiply, if you add 2 rows, you can make this as a sum of 2 determinants. And if you make this as a sum of 2 determinants, and if you interchange 2 rows, you get the minus, and if you 2 rows or 2 columns are the same, you get 0. And here we have the same properties with, but this is more algebraic. So if we interchange things, signs change. If we have two to be the same, the result is 0, and that's why exterior algebra determinants are linked so much. And now I will define, in fact, the determinant from the exterior power. So let R be R module, commutative link with unity. V be an n-dimensional of R module. N is integer, of course. And F be a linear map. Oh, when we have a linear map to itself, it's sometimes called NV, the space of endomorphisms. So this is endomorphism. This is nothing new. It's just when the two spaces coincide. It's called endomorphism. Okay. Then lambda NV of F is a linear map lambda NV to lambda NV. What's the dimension of lambda NV? But this is the whole power. I asked the top dimensional. So dimension, dimension of lambda NV is n over n. N choose n. This is 1. Yes. This is 1. Therefore, this is 1. Therefore, so a linear map from one-dimensional space to itself is something multiplied by a constant. So lambda f is a linear map from a one-dimensional space to itself. Module, okay, module. Now, if you have one-dimensional, it has some basis A. This should be lambda E1, some coefficient. If I multiply f of C of E1, it will be lambda C of E1. And so the coefficients will be the same. Therefore, there exists a unique, of course, lambda in R such that for any alpha in lambda and V, lambda and F applied at alpha is lambda times alpha. And we call this alpha this lambda, the determinant of F. Here we have found that the determinant of F is equal to the determinant of the matrix when it's wrote in a basis. And so, yeah, the determinant of F. This is the notation. Why is different than the standard definition of determinant of a matrix? Because this definition does not depend on any choice of basis. I only have to know that dimension is n. If you see, we have no basis here at all. Yeah, we have the following proposition, let's say. That she asked me for some homework. Maybe the proof of this can be a homework. Maybe for lower dimensions, check. For 3, I don't know. Let R be commutative ring with unity, and V n is integer, and V be an n-dimensional R module. F is a linear map, is endomorphism, is a linear operator from V to itself. And F and E from E1 to En is a basis of V. Then, if so, denote the matrix of the operator. So A is F of EE, which is n times n matrix. Then the determinant of F is equal to the determinant of A. So this is operator this is matrix. So this is matrix determinant, this is operator determinant. Now let's prove that the determinant of A times B is the determinant of A times the determinant of B. It's very, very beautiful proof and very short one. Knowing this theorem. B a commutative ring with unity. N is integer. V and n-dimensional R module. And F, so we have V, F, V, and then G, again G. Then the determinant of G composed with F is the determinant of G times the determinant of F. Let's prove it. So, let's take arbitrary. Let V1, Vn are arbitrary. Then lambda, the p power of G composed with F is of V1 to Vn is G composed with F V1, sorry, which G composed with F to Vn. Now this is G, so this is G of F of V1, which G of F Vn by expanding this one. Now we go back, this is lambda n G of FV1 to FVN. Yes, this is by definition. Okay. So we have this thing here. Now let's compute this one again. This is lambda n G, and by the definition of determinant, this is the coefficient that comes here. So this is lambda n G, determinant of F times V1 to Vn. And it is also, when you go back this here, and by the definition of determinant, this will be, okay, let's write it full. Determinant of A times G of V1 to Vn. And this is determinant of J. Determinant of F times determinant of J times V1 to Vn. So we prove this. And now I'll expand this as well. However, lambda p g composed with f of v1 to vn is equal to determinant of g composed with f by the definition of determinant of this thing here. And so we have this equals to this. So determinant of f times determinant of g times v1 vn is determinant of f times determinant of g times v1 vn. And we can, if this is a basis, if we choose the basis vectors, we can cancel out. This is true for all v1 to vn. So this is true for all v1 vn. So we can cancel. Because if you take a basis, this will be cancelable. And so determinant of f times determinant of f times determinant of g equals, sorry, this is determinant of f g composed with f is the determinant of g composed with f. So what did I do? I expanded the definition g composed with f v1, expanded the compositions, but then decided, okay, let's for g go back to the initial definition with lambda ng, and for the for the f I use the definition of determinant, and then I moved this back and did the same for lambda ng, and so it becomes determinant f times determinant of g. But I could start from this and expand the definition of determinant outright. So I will get this thing here. And I will get two things being equal. These are arbitrarily, and if I take basis vectors, I can cancel. So I'll get this thing here. And so this is a coordinate-free proof that the determinant of product is product of determinants. Okay. Now I have a few more things to talk. The dual algebra and the interior product. So this is interior product. Let R be a commutative ring with unity. And V be an R module. And so define the interior product is the unique let's say linear map. It's family of linear maps, but then keep them made a linear map to the whole space. But it takes a vector, so then takes an element of the dual algebra, lambda p of v star, and returns one with dimension p the minus one of v star. such that for p equals to 1, so p here is from 1 to n. I forgot to say. For p equals 1, we have the interior product and v is in v. So v is a vector, and lambda 1 of v star is v star. We have a covector. So omega is lambda 1 v star, which is v star. So this is a dual. And so the interior product of v with respect to v of omega is omega of v. So we have, so this is a, so we have a dual vector, dual element and a primal element, and you apply the dual to the primal. So we have the graded Leibniz rule, so called. If for p and q in integers, v in v, omega in lambda p v star, and eta in lambda q v star. The interior product, so the first argument is usually wrote as an index here, lower. So it is EV of omega wedge eta is IV of omega wedge eta is IV of omega wedge eta plus minus 1 to the power of p. We will have such kind of formulas very often. Omega wedge E V n et. Let's give example. These are squared. Let's say, again, I have the basis, so I will not write. So I have E of E1 applied at E1. This is E1, the superscript E1 at E1. And this is 1 by definition. Okay, let E1, E2 basis. I have also E of E1, E2 is E2 of E1, which is 0. And I have the similar things for when this is E2. Now let's move to E of E1, E1 wedge E2. So I am the dual algebra. And this is IE1 of E1 wedge with E2. And this is of degree 1, the left side. So this is minus 1 to the first power. E1 wedge E1 of E2. Okay. This is 1 with wedge with E2. Okay. This is 1 with wedge with E2. And this is E1 wedge with 0. So this is E2. And for the other part, we have E2, E1, E2 is E of E2, E1, which E2 minus E1, E2 of E superscript E2. I just forgot to say E1, E2 is dual basis. How much is this? 0. So this is 0 which E2 minus, how much is this? Yes, this is minus E1 which 1, which is minus E1. So you see E1, E of E1 of this element is plus E2, but when I get E2 is minus E1. I just want to state two things and finish. I hope nobody evicts us. So consider R module, commutative ring with unity, VB on R module. Then we have two things. First, for any V, for any V, for any V in V, EV composed with EV is 0, which means that IE for any if V is in V and omega is in lambda E of V star, then EV of EV of omega is 0. You see here, if I applied E of E2 twice, I have E1 and it will become 0. And here, if I apply E1 to this result here, it will become 0. And this is true in general. And second, the map the canonical map P, people usually make them equivalent, and that's why. So we have lambda P of V star to lambda. So we have the P vectors of the dual space, or the dual space of the P vectors. The canonical map is defined the following way. So P of omega 1 omega 2. So this should be applied to a P vector in V. So we have, so let's say the following. So if omega 1 omega n P are in V star and V1 P are in V star and V1 to VP are in V, and is defined as follows: P of omega 1 omega P by x1 wedge, sorry, here, wedges. So first I get p vector here, and it should become a function of p vectors here. So I have a p covector, and return factor of p vectors is defined as e of x p composed to e of x1, I reverse them, of omega 1 to omega p. So this canonical map is an isomorphism when V is finite dimensional. Sorry? Yes. This is the canonical map. It's defined everywhere, but it's an isomorphism when V is finite dimensional. And so we only have, so we therefore have also that lambda, the whole algebra of V star is like, is isomorphic to the dual space of this algebra here. Let's give some homework for people who want to try something in the previous proposition. Prove that we have the determinant that so phi of omega 1 which omega p of x1 xp, which was defined by so this is given by definition, the first equation by definition omega 1 omega p, and then I want from you to prove, so homework, that this is the determinant omega 1 of x1 to omega 1 of xp omega p of x1 to omega p of xp. Should be something like that. You should use the graded rule. So let me give example in 2. So e of x to x1 omega 1 omega 2 is, so we apply this first here. So this is e of x1, and if x2, we have omega 1 of x1 times omega 2, and we have minus omega, by the previous calculation that I did, omega 2 of x1 times omega 1. And this is omega 1, sorry, this should be omega 1 of x1 times omega 2 of x2 minus omega 2 of x1 times omega 1 of x2. Yes. And this is determinant. This is example in 2D. If you want to try, I'm not sure how hard it is, but in general case, this is the formula. Okay, let's finish here. If any public questions? No. Okay.